When we started the Humanity Centered Robotics Initiative, roughly 2 years ago, one of the things that we realized is that there was kind of three spheres that needed to intersect for us to really make progress on this problem. One was social, which is interacting with people. One is the physical world, so actually having something that moves in space. And one is decisions, intelligence, computation. And all the groups had to worry about all three of those things. And so even though we brought together a lot of professors at Brown and RISD to talk about humanity-centered robotics, nobody was really working in the intersection of those three. It was some people working on the computation, some on the physical stuff, some on the social stuff, and you guys have had to face the problem of making them all work together. So I think that's great.
Yeah. So should we go ahead and get started? Maybe start with the first group. This is the Beastiebot, and I will turn it over to the group for their presentation.
All right, so I'll just start talking then first. Do you want to pull up the slides?
And one other quick thing. So we want to keep the presentations to roughly about 15 minutes, give or take. So we have about 15 minutes to talk and to...
And the demo.
And the demo, yeah. And so we just have some time. We want to keep each group to about half an hour. There's a little bit of wiggle room there, but we'll...
How much time do you want, Pat?
5 minutes.
Okay.
Okay, cool.
So we don't really know what the name is. Sometimes it's Beastiebot when we put the speakers in. But we started out with this idea to create the Beam++, which is kind of like a play on C, C++, the next version of the Beambot, where we took all the things that we wanted to see in the Beam, such as an arm, head and neck controls, as well as an interface that's more suitable for a human being, and brought them all together to create Beam++. And there were three main components: design, swivel, and control. I'll talk about design, which includes the base, which is kind of the feet, the body, and the arm. So this is just a few of the iterations of our base and body. We started out the first day with this design, which we realized was going to have a couple problems with it. For one, we didn't want to have so much weight, and we also thought that we were going to have full range of motion with the camera and didn't want anything blocking the front, so that you could look all the way down and it wouldn't be blocked by anything you could see. We built a full wood prototype just to kind of tape it to a Roomba and prove to ourselves that it wouldn't fall over, it wouldn't be too floppy and top heavy. And even though it was really terribly put together, it proved our point that it wasn't going to fall over with a base that size if we kept it really thin. So we kept kind of going with that. We realized that the arm needs to be mounted in some way that wasn't these two blocks and hinged between it. We had a couple ideas in there, and they didn't really work out. I'll talk about that after. So we decided to add more support behind it, and we switched from two poles to a V shape, and that's what started out here. And we really liked that idea a lot, but we were concerned about it being structurally sound, so we thought it might be a good idea to add a wooden spine. But we didn't really like the look of the wood, and Ian had told us time and time again, if you bend the acrylic, it'll be really strong. So we trusted him, we went with it, we took away the metal bolts here, the metal brackets, and the wooden spine, and we continued on just with the acrylic. But the problem with the acrylic is it didn't have enough space for us to build shelves, which we needed for the arm and the top. It was getting too narrow. We thought this would be good for weight and just for aesthetics, but it turns out we needed more space. So we went all the way back to foam core, and we built this model, which involved a back that was scored and bent. And we realized that also we could do this with the Roomba, because this is where the Roomba base, where the dust container would be. So once we took the cap off the Roomba, we had this whole open space, and we kind of really liked the shape, so we tried to go with it and build here. We were all really afraid of the scoring because it involved a lot of acrylic bending, but it was actually really rewarding because we ended up using this. It ended up being really sturdy, and we were able to put shelves on it fairly easily. These were also the bottom sizes that we tried to go with. We started with a circle, we took a little bit out of it, then we completely reshaped it by putting this triangle with a square, and then we ended up with this horseshoe crab shape that I mean, conveniently enough, was just the same shape as the Roomba without the cap on it. So here's just some of the arm iterations. This was the first one on the wooden one over there. It was just basically a big piece of foam core with a 3D printed knob at the end. What we took from that was the pointer tip. We still have the same pointer tip now. Then we tried a better hinge because that really was not hinged well. It was like duct tape to a chopstick. And we just kind of pulled the back with a string. So then we tried bending these acrylic pieces and putting them over a metal pole, which was a really great lesson in bending acrylic. And it worked pretty well, but it was also kind of wonky, and we wanted it to be a little more sturdy than a twisted piece of acrylic. You can pass this around if you want. So we kept the acrylic and we moved on, and we realized that we needed a better way to hinge it because it had to be attached to a motor somehow. And this wasn't going to be attached to a motor very well. We put a hole through this, but it was still kind of weird. So we tried this like Snapchat ghost shaped thing. We put a string through here and pulled it, but it was still like too floppy side to side. And when we wanted it to be able to press an elevator button because that's something the beam couldn't do. And when you would push, it would flop. So Miles thought of this great idea to put another hole here and have 2 strings in each side so that it would have a certain length of string and it would be taut at all times. It would go up, it would reel in the back string and give a little more in the front. And it was great. It was really sturdy this way, but it was really floppy this way. And we didn't like that at all because when you're trying to go up against a button, you don't want it flopping around. You want it to hold still. Plus we also were kind of, this was also sort of not the best way to attach it. So then we finally came up with our last iteration, which is what you'll see when we demo. We moved the motor to the hinge on the arm so that the motor, we don't know why we didn't think of this sooner, but the motor is just basically sitting at the arm. And, oh yeah, first we had to attach the whole arm. It was really wobbly, it was hacky, it was funky, and we didn't like it. So we took away that, and it was distracting from the middle of the body. It was like right here. So we will, yeah, this was the formal language we came up with. We learned a lot about design. We're all ex-engineers and current CS, or ex-engineers or current CS, but most of us are CS concentrators. And we came up with this formal language for our design. We had blue and yellow acrylic, black plastic. We had exposed wire, exposed chips and everything, so we didn't have to hide any of the motors. There was also just this, like all bends and curves of acrylic, and all of our, bolting and the screws, they're all exposed in like a techie field. I think that might be it for what I left. Yeah, so Aaron's gonna, do you want to demo now? Or do you want Aaron to? Okay.
Here, can I see that, Aaron? Real quick. Just get this calibrated. Hi everyone, I'm Aaron, and so when I came up with this concept, I mainly wanted to have an extension of the human neck, and I'll go back. So this is a picture from in Africa. It's a giraffe. Its neck is skewed. That's kind of what we want to do with the swivel. The swivel over there, if you can look at the top of our robot, that's like a representation of our neck, or a telepresence of our neck. And the headset has an accelerometer on top, which can record how your head's moving, and then send that to the 2 stepper motors that are mounted on top of each other, controlling a phone, which is in a video call with another phone in front of your face or on your hand. So headset iteration 1. I would describe this design process as like kind of like this. I start out really, really complicated, and then I really simplified things. So the first iteration, I wanted to have all the electronics mounted in the back. So these, so this headset, this is the front, and then this is the back. Your ears go in here, and these loop on. There's two of these beams that go over your head and then hold a phone in your front and in the front of your face. The antenna comes out of here. So aesthetically, I really pay a lot of attention to it. But then I realized that mounting the actual electronics would make it slightly less convenient. And like another touch to it was having my own patented bearing inside. So here in the antenna hole, I was thinking of a way to how to tighten the headset on your head, because this is just a joint here, and they could slide off. So if there's a one-way bearing in the top end and the bottom end, then you could cramp it in, and then it wouldn't go outwards. So this is the second iteration. You can definitely see that it simplified a lot. It's just the only thing that you need on your head, the accelerometer, and it's attached like an earring. It just kind of clips onto your ear. It worked, but then I still wanted to have everything on your head, like one piece, because this would essentially move all the electronics to other places on your body, like having batteries here and Arduino here. I didn't think that was a really good plan, so mouse. Iteration 3, it's pretty much like a middle ground between the two, fit everything on the head. And the hat, the two acrylic pieces can mount onto any bill, as long as it's a flat bill, and it's a hat, so it's easy to put on and off. The driver unit, so this is what we have right now. These two pictures, these are just GoPro clamps, and if we weren't mounting the swivel onto the robot, we could put it anywhere else. We could mount it onto the edge of a table using something like a GoPro clamp, or onto a car. So if we weren't using it for the robot's purpose, then it could have many different clamps, as long as there's a fixed surface for the two-stepper motors to mount to.
And real quick, we're just gonna run through the controls as fast as we can so we can extend the demo. We have this chart that talks about. Oh yeah, good.
Okay. Yeah. So, hi, I'm Pat. I took care of most of the coding for this, all the communications between sort of the different components. So our stack is Arduino and Python. Arduino is sort of everything that is, we have. I guess maybe I'll explain it a little higher level. So we have two computers. One is the one that is piloting, and one is the one that is mounted to the robot, which you'll see real quick, or real soon. We have a client running on the pilot computer that sends signals for the movement of basically the movement in both directions. So both the movement of the robot itself and the movement of the arm. We have a controller that Denai hooked up that allows you. It's basically like a handheld mouse type thing that allows you to control it pretty naturally. There's a trackball and a scroll wheel. So the trackball controls the movement of the robot itself, and the scroll wheel controls the movement of the arm. And we also have an Arduino, which sort of skips that step, that's mounted to Aaron's head. It is transmitting directly to the computer on the base. Ideally, we would have had it transmitting directly to the other Arduino. We got close to there, but we sort of, the computer was much more reliable. Using an Arduino as a server is not reliable. So that skips that step and goes right to the computer. Then that computer has a server running that sort of takes in all those inputs, parses them, and sort of processes them, scales some different things, like, for some reason the Y direction needs to be scaled up and the X direction is super sensitive, so we want to turn that down, and sends it to the different components on the robot itself. And I think we should probably go ahead and start the demo. Is the swivel good? Is this fine? Yeah, it's fine. All right, cool. Should we bring it over this way, or? Why don't we telepresence? Why don't we have it drive out? So, yeah, do you want to... Classes had no homework! Back up. You gotta find. Yeah, okay. So as you see, Aaron, maybe you want to pause and turn your head. So as he turns his head, this is moving around quite slowly right now. But basically, it's supposed to mirror the movement of the head to look like you got a little bit out of calibration, but it was pretty slick earlier. If he uses that trackball there to move the robot itself, did it just cut out?
Just cut out.
Okay, and then the scroll, the Wi-Fi has been a little shoddy. And then the scroll wheel on the mouse. Do you want to try moving that? The scroll wheel. Okay, yeah. I'm gonna reset this real quick.
While he's doing that, can you tell us what there's? Things are spread out all over the place. There's something happening here and there and there. Oh, okay, never mind.
So Aaron, it might make more sense if you drove from here.
Yeah.
Drive from there and drive it out.
Aaron, sit over here.
You want me to stand over there?
No. Stand
Because
there.
this is where I'm supposed to be.
So Aaron's
Yeah.
being the pilot
So
now,
I'm the pilot.
and he could be anywhere in the world as long as he's right there.
So this could be a phone. This could be an iPad or a computer. These two, this and that phone are in a video call. So my face is shown on that phone screen, and I can see what's going on over there.
And what is this?
Supposedly, okay, so this is like my
Is that what's on your
virtual-
screen right there?
Yeah, this is.
Okay.
So this is this is the same as the screen. So when I turn my head, the swivel should be able to turn in the same direction.
Yeah.
And then the other way, vice versa, up and down. So the point of it is to have like a more natural way to control what you see, instead of like having like WASD controls. So having this is the ideal. The ideal stage would be as if I'm turning my head left and right, and then the screen in front of me is also moving left and right at the same pace, and I can see pretty much the same field of view. So that's where we want to be. But right now we have, because it's an accelerometer, it can't tell how much we turn, so we have to tilt. But the tilting also solves another issue, which is having the extra screen up here. If we tilt, then we just kind of have to look down here. We don't, because if we want to look left and right, then our eyes move away from the screen, and we have to move to maybe a phone screen up here, which is a lot more tedious.
So the basic idea is that we want to have some sort of motion that's really intuitive and natural. And so on the one hand, that means having a screen which right now is right in front of him, but at some point in the future could be moving with him, and controlling that screen and the view field with motions of the head. And at the same time, because we're looking to incorporate this sort of mobility that doesn't require him to be seated at a computer, we have a control that's held in one hand and has 2 degrees of motion. One is a scroll wheel, which moves the arm up and down, and the other is a trackball, which allows for greater degrees of freedom and actually moves the robot through space. So with these 2 parts, we're looking to basically achieve something that's, right now not quite, but in the direction of, complete mobility and not needing to be tethered to any particular place.
So is the plan to bring it out so we can see it?
Yeah, right now we're trying to reconnect the swivel so we
Okay.
can show like a better demo of the screen actually moving.
Yeah. It's sort of a little bit finicky. It kind of needs to be calibrated.
Can you give us a
Okay,
sense
did
of
you
where
do
the
the
finicky
driving?
points are? Is it mechanical? Is it electronic?
It's the
Is it-
connection.
It's Wi-Fi.
Yeah.
Cool. That's it.
So-
Here, can you stop driving?
Yeah. Hold on. Careful. With
Smacking him in the face.
Oh, Pat, you're probably hitting the connections in and out of this.
So another point about the swivel driver unit, we wanted to keep the camera on the same center axis as the 2 stepper as the bottom stepper motor. So then when we turn, like the camera moves at the same level as your head. So that's why we the mount for the. I'm not driving. I'm not.
This is a note about hardware. This trackball is like a little bit sensitive, and if you just move the device, sometimes it'll send signals.
We've been slapped in the face by the arm a couple times.
Have you actually tried to push buttons on
Yeah,
either?
we've set up buttons like a screw with a washer on it, extended from a piece of wood, and it will press those.
It does. Cool.
Nice.
We just couldn't take it to the CIT because it's been raining
Yeah.
quite a bit.
There are elevators.
And it has a good amount
Oh
of.
yeah.
Just for future
Okay.
reference.
Yeah. Well, the goal was
No,
to hit the
it could
highest
begin-
button in the elevator
Yes,
of the
okay,
CIT.
so-
Right. Yeah. This
Okay,
is,
guys, Aaron's gonna wrap it
I'm
up.
gonna show the swivel again.
So do you want to scooch?
So when I put my head down, okay, right now it's
You move it
fine.
down.
It's on.
Bring it over here.
I'm gonna move my head up. It moves up.
Can we take this off?
My
Uh-oh.
It's really hard. Alright, that's the other way.
Yeah.
So I'm driving it backwards right now. Tilt my head. Looking at Professor Bull. Tilt my head the other way. Turn my head back.
Really like the robot out here. If you could bring it out front.
Do you want to just carry it?
well, yeah. I think this might just be a little tight.
What's cool is you don't have to look in the direction that you're driving per se. You gotta like look around just to not.
It's like that's not right. But
It's shiny.
so I'm gonna turn my head. Up. I'm looking at Professor Lippman.
You want to high five you in?
High five me.
Fix the connections.
Oh, it broke again.
Just the wires connection is. Yeah, we also.
That's had to happen.
So,
Perils of doing live demos.
Yeah.
Oh, I want
Oh.
another.
Dist!
Alright, I see how
High
it is.
five. High five.
Yeah, so we sort of bound it so it can't go too high. We basically have ranges and we don't.
okay, I just lost
Just the arm wire came out.
Yeah, so the arm wire, we tried soldering it. We tried taping it, didn't work. We tried soldering it. Similarly, it was difficult. So that's one point where we'd like to sort of be able to have that more secure, because just with all the jiggling that goes on, you know, it can sometimes the wires connected, the leads for the Arduino pop out a little bit, but yeah.
All right, so I'd be inclined to do whatever other feedbacky thing we're supposed to do next. Aha! Exterminate.
So I think you guys did a really good job of, first of all, just kind of talking about the process, talking about the different areas that you've identified, which, if we back up a little bit, we kind of began the semester in different groups. In in this.
Back all the way.
And kind of trying to, I think some of the original ideas from this came from the initial experimentation with the Roomba, and then there was like the Mica. Was that kind of
There's elements of that group that are in this group, but it fissioned a little bit.
It fissioned. So I think what was really great is that about mid-semester, you guys were able to identify these several different areas that you wanted to work on. And one was the locomotion, one was the arm, and one was the swivel. And I think that you guys, there were some considerable technical challenges, as well as kind of just figuring out how to fabricate this thing. And I think on all fronts, you guys did an excellent job of of identifying those challenges and then navigating through it. Not to say that there wasn't some frustration along the way, and there weren't times where we were pulling our hair out, but look at what's here. I mean, this is actually doing all the things that we designed it to do. So that's just a kind of a recap of kind of the arc of the process as I see it, but maybe we can invite our guests and the rest of the class to kind of comment on what we have here.
Well, first off, really impressive to see this thing actually moving and the arm going up and down and everything moving around. So that's a great achievement in the time that you had to work on it. It's really pretty impressive to see how far you came in the length of time, and I agree with Ian in terms of what you presented and how well you presented it. It really covered a lot. I mostly right now have a couple questions, and the first one is, if you had more time, or what the next steps would be in terms of making on the interface aspect of it, how would you improve that? The tilting, instead of turning your head, seems like it would take some getting used to. So what would it take to get to a point where you could just turn your head?
So using a gyroscope gyroscope could detect your position.
You'd have to orient one of them perpendicular too, so that you would.
So right now, the accelerometer only detects tilt. If we turn, it has no feedback to that. So first we would switch it to a gyroscope, and then change the motors, so then we can have like a wider field of view. Because right now the motors are not strong enough. We want to switch to 68 ounce per inch stepper motors. So right now they're not strong enough, and we limited the tilt, or how much the motors could spin.
Yeah.
So that's why you can see that there's only like a very minimal change in the field of view. So if we change the motors, then we can definitely like put the phone flat and then all the way back.
And we had talked about using gearing, like a gearbox, to
Yeah.
kind of take up on that as well.
So we tried one of the 68 ounce inch stepper motors before, and actually is strong enough, but then it's just not consistent. The Arduino driver for the Arduino driver that we're using isn't strong enough to drive the stronger stepper motors, so that's why we're using these weaker ones.
And in terms of the interface too, if you're able to turn your head in a wider range, the issue becomes that the screen in front of you, which right now we just have on a computer,
Right.
like that's not going to turn with you.
Right.
So what's really cool about this is that it basically just like latches onto the brim of this hat and it can mount anywhere. And what that would entail if we were to improve it in that way would be to mount also some sort of screen there that could also come off of the entire piece.
At the very beginning, we also were kind of thinking that it would integrate with Google Glass, which no longer has the video calling feature. So that
It's really
kind
hard
of,
to
yeah,
do that.
we were not going to rewrite video calling.
Right.
But if you had something like Glass, which has a built-in gyroscope, a built-in accelerometer, and this video feedback,
Yeah.
Which is where we
then-
kind of started at the
That's
beginning.
right.
Yeah,
of
that
this
was like
semester.
our kind of like our inspiration right there.
So I think that this kind of came out of an attempt to mimic that, which I think I mean, we can't reinvent Google Glass, but I think that this does what you guys wanted to do, and it
Yeah.
works technically. And I think there is room to improve the user experience, but I think just getting this to kind of work the way that it is a huge success.
Yeah, just the other thing would be sort of more testing, figuring out that probably have different programs running controlling each piece would probably make it more reliable, I think. So rather than just having sort of like one program doing everything and just spitting out signals left and right. Another thing would be cool would be to get sort of the network hooked up to the internet and be able to actually have one computer doing everything. As you see, we have to Skype from the other one because it's on a local network, but it's not. But that network is not connected to the internet, and both of Brown's networks are secured in one way or another. So that was.
There were a lot of challenges, of things you don't see in the actual robot. I mean, the Wi-Fi was that was a huge thing, trying to find a solution to that. But you guys figured it out,
We've seen that with the actual game.
It's true. Yeah. Even the commercial ones, it's sometimes a little bit iffy getting it to talk to the rest of the world.
Installed the microwaves in the CIT because they were interfering with the actual.
really?
Sorry, can't heat up your food. So one thing that Skyva challenged for you guys. So I think this is fantastic. I'm really very, very impressed at the how far you were able to get. One of the challenges in getting the robot to actually use the elevator that I know you didn't go after yet, but if you have any thoughts, it would be great to hear. So I could imagine driving this, swiveling my head and whatnot, and pushing the elevator button, waiting for the elevator. I do imagine it would be hard to get on the elevator because I don't know how much clearance you have on the wheels.
Yeah, so actually we drove over pieces of wood unintentionally, and it was totally fine.
Okay, all right.
It's all
Once you're
terrain.
in the
So we drove
elevator,
over like lots of clumps of wood over there while pushing the button
Nice.
that we made up.
yeah.
And like
It didn't fall over.
Okay.
it didn't fall over. It was pretty high up, and I was thinking about the elevator, how it would work, and I think we would be fine.
Okay, so that's awesome. Inside the elevator, you turn, you face the buttons, you put your hand up, you close it, the doors close, and you lose Wi-Fi, guaranteed. So what do you imagine from a user perspective would happen then?
I think one approach to do it, I think we could have either time it or have a sensor on the have our hand reach out once we get in, and then once the door rolls and we sense that the door, like if there's a wheel here and then the door rolls out or opens, then it rolls our sensor, and then we know that the door is open.
Yeah, if you
And it's
added a
automatically
sensor on the
discharged.
front.
I would note that also in addition to technical solutions to that, there are also social solutions to that, which are, if you're getting in the elevator with someone or there are other people around, if you're navigating a robot like this and the other person at this point can't actually see you, but if you could speak to them, you can make a sort of social contract. And
They
have
can
someone
see you,
else-
though.
It's-
Well, they can. Right. Sorry.
Yeah.
I said. Yeah.
The oil can syndrome, like Wizard of Oz. Oil can.
Right, right.
Move me on there.
Yeah. So
Okay.
I think that there are other solutions too.
I think it's really great, and you guys obviously have had a lot of fun and probably heartache over it too. I'm guessing. My comments are more just as a newcomer to the project. It would have been great to have some sort of framing at the very beginning. Like it wasn't until you said like the goal was to get this thing into an elevator and push a button. Is that right? Or push the
Yeah.
button,
Well-
call the elevator, and get in. So that would have been really useful for me. Even as judging it as how successful it is on a broader scale. I know you guys are focused on the nitty-gritty, actually making something work. Trying to understand from a user's perspective, and I guess I'm using that term, the user is the person who is trying to drive this thing remotely. Even some indication of why they would want to do that and what this thing does. And I think, I'm sorry, I don't know your name. Denai. You talked about sort of the social contract. I think those are really interesting questions, again, in the broad spectrum of sort of where you're going. What does that mean to be driving something remotely? What is that person doing, like this sort of the motions of the head? Like if I'm talking to you and I'm going like this, it does seem kind of could be very off-putting. So whether someone, when they're engaging this and humans at the same time, it's interesting to think about what kind of impact that has. The thing about it hitting you by accident, I think that's very funny. It does bring up the Doctor Who analogy. But thinking about what does that arm mean, is there more of a social interaction? Could there be, when it's, just right now it's just basically this thing that sticks out and you can ram it into the button, is that correct?
Yeah.
Is that how it works? But for the other humans in the elevator, it's an interesting question as to whether there are ways that you could modify the arm so it's A, not physically dangerous, but B, the high five gesture. That's kind of cool. Maybe there needs to be another end on it that can, right, that can do this. So it's the human side of it and the interaction, which I think is just, it's fraught with possibilities. Your decision making with all of these very technical elements can also always, every now and then it'd be great if you can sort of come back up and think about, okay, what's the goal? What's the interaction? What am I really trying to achieve? Yes, push a button, get on an elevator, but it seems more like this would be a remote me somewhere. So just kind of taking those breaths every now and then, and it can help you in the decision process as you move forward. I think it's great.
And this is sort of how we started, was sort of framing the problem, and we probably shouldn't have done this for the audience. But we had a couple frustrations with the current beam. One of which is that you 100% need somebody else to do any of these things, right? Go through doors, use the elevator. So we were thinking with this arm, you'd be more autonomous. You could actually explore space. We are actually going to try to do a map as well, some sort of, be able to see where you are. So because we think the addition of the beam over Skype is that you can move around. What this would allow you to do is move around an unfamiliar space and experience it there. The other thing that the swivel does is I've had meetings. So last semester and now Miles is the head TA for artificial intelligence in the computer science department, and Stephanie Telex has a small child, but sometimes she would beam into our meetings. The thing is, for her to be able to look around in a meeting, she has to use these two things and back up and move around, and it's completely distracting. And so that was sort of one of the problems that the swivel was trying to solve there. But yeah, those were sort of some of the things that we were trying to target from the human side. But yeah, I think we sort of dove down towards the technical things in the last month or so.
The swivel is meant to work as a standalone unit, but here, as I was talking about the mounts, if we wanted to use it, say, in a meeting, then it would be on, maybe weights and then a stand. It's just some sort of base that can hold it down. And we would have another phone here, or you could even use your iPhone. We also chose to use a phone on that end for a reason, not just a random camera, which would be actually a lot lighter. A phone is, everybody has phones, you can call each other, it's very easy to connect. So,
and you want to develop this further as a standalone item.
So, say we have two people, one here, say I'm calling my parents in China, They have a hat, they have a swivel. I have the same setup here. I can control their unit. They can put their phone on it. I'll put mine here. And just like what Professor Lemons.
So we're almost out of time, and there was a couple other things I wanted to hit on before we close up. I know that Denai was itching to say something about the human contact. Are you okay with that?
Well, so I'd say basically we were focusing on the user from the perspective of someone actually driving it, like the pilot's interaction is more what we were concerned about. Because we started this class basically with a lot of discussions about what it means to be present in a space at a distance. And we thought that sort of from the pilot's perspective, the most pressing issue was just that there was a really limited level of autonomy there, and we wanted to address that first before delving into then how that person would integrate into a more social setting.
Thanks. So one thing that I'd like to point out is this group in particular was very computer science heavy, and so just as they've talked about, I think Wendy mentioned the formal language aspect of it, just getting them to think about it's not just it's not that. It's not just the wooden thing that just it does structurally what it needs to do. That it has some coherence visually. They came a very long way. I'm very, very pleased with the progress. Is there anything to say about what it will be able to do tomorrow? Is there anything between now and tomorrow that we can get a sense of how it's? No, you're just going to sleep. All right. And maybe
There's only so much we
connect
can
that
do with the
wire.
network. I feel like that's
Yeah.
the bottleneck.
The network.
What I'd like to do tomorrow,
It's very helpful nonetheless.
and this is applicable to all the groups, is I'd like to have a little demo, and we can continue the conversation a little bit when we're not so constrained with time, and we can also talk more individually. But I think, just to reiterate what everyone else said, I mean, tremendous, wonderful job. I mean, you guys, there were frustrations, but you guys navigated those really well, and you came up with something that works the way that it was designed to work. You identified the need, and I think you guys did a great job. So, good job.
So do we clap? Yeah.
We
okay.
clap now.
All right, so we were not really sure what our name is, but we have two as of now. Beam++ is the name we gave ourselves when we started because, like a play on C++, what we wanted to do is take the beam a step further. We noticed that some issues with the beam involved the fact that you need someone else to operate it, even if you are telepresent, because there's no arm, you can't press an elevator button. And say you're at a table at a meeting in the beam, and you want to look and turn and face the person who's talking. It's actually quite distracting. You have to move up, turn, and watch them. We wanted you to be able to just turn your head or turn the camera and be able to see next to you. Also, we wanted it to be more of a human interaction. So rather than sitting with arrow keys and not being able to move around at all, we have a handheld controller that looks like this, which controls both the movement with here and the scroll wheel controls the arm, as well as a matching hat that mimics your movement with the gyroscope. So you can, like that, you can tilt your head to turn left or right. We did the tilt because if you're looking at a screen, you don't want to turn your head away, because then if you turn back, your camera will turn with you. And you can also move up and down. So you can look at your arm, you can look at the ceiling, which is another thing you can't do with the beam. Good? So it's like a whole thing to set up here because we wanted to be able to control it completely remotely. That was a main goal. So we have like a laptop in here running a Python server, and everything else is just Arduino and Python. Oh, and the reason we gave it the name Beastiebot is because we were able to put speakers in and just have it drive around, kind of like Parks and Rec, DJ Roomba.
I'm gonna talk briefly about the swivel part. So from the very beginning, I wanted it to be also used as a standalone unit. And so if you can see through the acrylic here, there's an Arduino with a Wi-Fi shield. And there's the same setup over here on my head. There's an accelerometer on here that can detect my head's movement. And so it sends all the signals to the Arduino over there to control the two stepper motors, which has a camera and a screen on it. If it's used as a standalone unit, then there would be another screen here, preferably maybe a phone that would slide right here, and you could see. So you could see what the other phone is showing. So say I'm in a video call with my parents in China, they would have the same setup there, and I would be controlling the phone on their side. They would be controlling the phone on my side. So it's an extra level of control over what you can see during a video call. Instead of just the person holding the phone, you can look around naturally, almost as if it's like an Oculus Rift, but a more accessible version.
One second. I think what else? It's sitting on basically a Roomba, and we were able to control the movement of the Roomba, so we use that. There are a couple models of ours back there. We tried a lot of different things with the arm. A couple days ago, like super recently, we realized that the best thing we could do is just put the motor at the hinge. Before that, we had all different funky stuff with strings to keep things stable. We ended up adding an I-beam across the arm so it didn't wobble this way because we wanted it to be super sturdy to be able to touch an elevator button without it swaying side to side or while you're walking going like this. Oh, there we go. Oh, because he's tilting his head.
And then let me just test
It's just one way or the.
Did you actually try to hook it up with an object and stream the video?
In the beginning, we wanted to use Google Glass, the video call, because the Google Glass has gyroscope, accelerometer, everything in there, plus a screen on the side. But our main challenge was that Google Glass removed the video call feature like a month before we decided to do it. It would be really hard to write that for ourselves, so we decided to just take it to like the Arduino setup with the gyroscope, accelerometer actually, and we were gonna have a phone here, but considering the use with our Beastiebot, our controls would be on the screen. We would be calling, and there's another controller, so we could put the video call straight onto the laptop screen. So if you weren't using it with the Beastiebot, then there would be another mount here for your phone to slide in. And then there would be another phone on that side that you can screw on and take off really easily right here.
Swivel's up. It was a second ago. I think that's just resetting the network.
One of our biggest challenges is getting the Wi-Fi communication to work consistently. But once it works, it's pretty stable. Once you get it connected, and when you move your head, like when you're looking at the video feed, it's really smooth. So when you tilt your head, you can see the field of view move to your left or to your right.
Did you have problems calibrating the IQ?
The what? Yeah. Actually, yeah. Pat worked on most of the programming, but yes.
Can you talk a little bit about the formal language?
Oh, yeah, so about us, we're all CS concentrators or engineers. So none of us have really done much with design, but we had to create a formal language for what would fit with the robot and what wouldn't. So some of the things that we made sure to keep track of is we wanted everything exposed, like all the Arduino chips and all the wires are all exposed along with all of the bolts. It's completely see-through. We use blue and yellow. Blue and yellow, and we matched that up here also. We wanted to put wood on or metal or something to stabilize here, but we realized it wasn't part of the formal language, so we couldn't.
Talk a little bit about kind of where you started and where you ended up.
Oh, at first we wanted to do something with like a wooden spine or a triangular base, or even just like a V-shaped base, because we thought that would be the sturdiest. But as we started to work on the arm, we realized we needed a lot of support on the top, and we also realized that attaching a triangular shaped base to that Roomba would probably not be the most stable choice we could make. So we went all the way back to the drawing board, and although the foam core thing looks like it's really old, it's actually our most recent model. When we realized that that's probably the sturdiest way to develop shelving and to develop some sort of back. There we go. So that's our most recent, and then we took the old acrylic and bent it and turned it into this. I'm gonna turn it around.
So possible next steps for the swivel, we want to switch the stepper motors to higher torque stepper motors. So then, because right now with the Arduino driver shield, it's like an easy driver. You can't really drive stronger steppers, so that's why we're using these smaller versions. And so our field of view is slightly smaller. We constrained it to only like this much, because if it bends all the way down, then it doesn't have enough strength to pull it back up. So that would be our next step. Plus, what's it called? Using a gyroscope instead of an accelerometer, because right now we're using accelerometer, and it can't tell if I'm turning like this, and really that's more of like a natural motion. With the gyroscope, you can tell like me turning like that. The accelerometer is kind of like this tilting.
She took me along again. Because she was my.
So we'll place this in there carefully.
I have to run.
There you go.
Well, it was working about a second ago, and then we put the laptop
fine,
in.
it's fine.
Now it'll start working again.
Yeah,
Great.
okay. So I, as the pilot of this, have a controller here. I have a scroll wheel to control the arm going up and down. Perfect for punching people. Wait, did you just cut the call?
It just disconnected.
Alright.
Disconnected again.
Alright, great. And I have a trackball here with which I can control my movements as I move my head. So say I want to look up. There's an accelerometer on here that's hitting that computer, and it's signaling to this device here, this Arduino under the mounted at the top. So if I want to look down, I can sort of do the same. It looks like the video call messed up, but yeah. So you can drive around, and the ideal situation would be that, like, say you need to get through a door. We haven't actually been able to bring this over to the CIP to test it on the door, but you could maybe press like a handicap button. You want to move that model out of the way? So you line it up, and then you could go forward, and then you could back up, and then go through the door. Sort of what we're inventing there. Yeah.
So the swivel, you can see this unit as an extension of your neck, and the hat captures what your head is actually doing. Yeah. So this displays. So you can see this unit here, the two steppers and the phone mount, as an extension of your neck.
Is that basically what he's doing?
Yes.
Yeah.
So
like, if I look up, that will point up. Ready?
Ideally, when you look up, then right now we limited it to a very small angle because the steppers aren't strong enough to pull the phone back up if it's all the way flat. So that would be our next step.
Like one of those virtual reality things. Then you look up.
That's what we were going for. Yeah. So in the beginning, we wanted to use Google Glass, but like working with Google Glass is really, really tough. So we decided to just take out the vital parts.
You should be in the cave.
in the cave?
You should be in the cave.
Yeah.
I should be in the cave?
When you do that, and then it looks up.
Okay.
You'll actually be up.
Yeah, if you guys want to take a closer look. Obviously, I would generally be looking through here, but. Here's my. Any other questions?
What's next?
What's next? Aaron, you want to talk about the swivel now?
So the swivel, from the very beginning, I wanted it to be worked as an independent module. So you can mount it on any surface, pretty much with like a GoPro-like clamp. So maybe a suction.
What's a
cup.
GoPro like?
A GoPro, like a GoPro camera. So GoPro cameras are used in like different situations. You could mount it like that. You could put it on a weight. So pretty much this base here right now is just screwed into the top of our Beastiebot because it's the most secure way to mount it. But if you were to use it somewhere else, then you can also mount it to maybe the edge of a table when you're calling somebody back home. And the part that I paid a lot of attention to is how you mount the phone. If you can see, you just screw this. You can unscrew it and screw it back on. And because it's a phone, like everybody uses smartphones, so everybody could use their smartphone along with this, and there's no connectivity issue. If we were using our own webcam on there, it would be a lot lighter. Moving it would be a lot easier, but it would just be harder to use connectivity-wise.
So So like one thing is, Stephanie, when you would come in for meetings on the beam, like if you couldn't really look around, right? And if you did, you would have to like back up and probably hit a table or something. So one idea is that this, like whether it's on a robot and you're moving around or even just mounted on a table, you know, you could easily sort of see around the room.
So I have more degrees of freedom.
Yeah.
Hat.
Yo, take that out. After a while,